on generalized inner product estimation with limited quantum communication.
This is a joint work with Srinivasan, who is a research scientist at IBM. The problem set that we will concern ourselves with is the following. Say that there are two spatially separated parties, Alice and Bob, and they each are given k copies of unknown states, psi and phi. Then our motivating question will be the following. What can they learn about the relationships between these states, psi and phi, with only limited forms of communication? To motivate this, let's look at a quantum network, where each node may consist of a different type of qubit, a different type of processing device. And let's say that we only have classical communication between these devices. Well, then the important question to answer is how can we verify the similarity of states on different devices? How can we verify that these devices can prepare similar things? And formally, what you may want to do then is to estimate the fidelity between these states. And this is something that has been attempted with real device data. More mathematically, the way that we'll phrase our setup is the following. So Alice and Bob will again be given k copies of these states. Alice can perform some measurement on her copies. Perhaps she gets outcome A. Alice can send that result to Bob, and Bob performs a measurement on his states, which is potentially conditioned on the message from Alice. And let's say he gets outcome B. Then Bob can send that back over to Alice, who can then perform a measurement, perhaps conditioned on Bob's message B, and so on. And this is what we would call local operations in classical communication, or LOCC. And this is a framework that has been well studied in the context of entanglement theory. What we will also consider, in addition to LLCC, is small amounts of quantum communication. And what I mean by this is the following. Say that Bob has some small number of qubits. He can send it over to Alice using some additional channel. And then the task that we will try to solve is the following. Given LLCC effectively is a free resource, so we'll assume that LLCC is easy, that classical communication is relatively easy, but only some small amount of quantum communication, or even none, we're going to assume that quantum communication is far more expensive. They would like to estimate some generalized form of the inner product. By this, I mean instead of the fidelity between phi and psi, we're now going to throw some other operator m in between these, and we'll estimate this expression here. And in addition to restricting the forms of communication, we would like Alice and Bob to be able to do this using as few samples k as possible. I mean, of course, if they were able to take enough copies, they could just do a full tomography of their states, right? In which case this becomes fairly straightforward. But really, we would like to get away with fewer copies than full state tomography. Let's look at some examples of what this could be. If we take m to be identity, then this is exactly the fidelity again. We recover that. And for mixed states, this is going to help us estimate the Hilbert-Schmidt distance. If m is a projector onto some subspace, then we measure the overlap just restricted to some subspace. And more broadly, this could just represent some sort of more general metric on d-dimensional Hilbert space. And then again, the central question to our paper will be, how does the allowed communication change the sample complexity of this task? We're really going to be concerned about the number of copies k of these unknown states. All right. And here is what we were able to show. With only classical communication, it was previously shown that roughly square root over d copies are sufficient and necessary to estimate the fidelity between two pure states. We will improve this to account for these more generalized forms of inner products, again, where we take some operator m and wedge it between the states. And we'll prove nearly matching upper and lower bounds for this case as well. And you can see that this is roughly controlled by the norm of some operator m epsilon, which we'll go into more detail on later in this talk. And then in a slightly different vein, we'll look at quantum communication, small amounts of quantum communication for estimating inner products. So this is when M is equal to identity. And what we were able to prove is that if they are allowed to communicate a Q-dimensional quantum state, then the sample complexity goes like square root D over Q. And we can prove that there's a protocol that will actually estimate inner products using square root D over Q copies and a constant number of Q-dimensional messages. So these are not exactly matching in some sense, but they show that there's some sort of smooth trade-off between entanglement and the sample complexity of these problems. And again, I'll get into more detail on this shortly. All right. So first, we'll look in a little more detail on generalized inner product estimation, where you're only allowed classical communication. Like I said, the goal is to estimate this generalization of fidelity using simply classical communication between the parties. Well, first, let's look at what happens if there's no constraints. That is, let's say that Alice and Bob can share unbounded amounts of both classical and quantum communication. Well, in this case, it turns out to be quite easy. And let's focus on just fidelity for a second. So if you just want to estimate the fidelity, then there's a very straightforward protocol, the swap test, which has been known for quite a while in the quantum information literature. And using this test, you can achieve a sample complexity of 1 over epsilon squared to estimate fidelity to accuracy epsilon. And it's not hard to show that you can modify this test just a little bit to account for these more generalized forms of fidelities where we insert this operator m. And then again, you'll be able to estimate this expression using only 1 over epsilon squared samples. So this is quite straightforward when you have unlimited communication. Well, now we would also like to ask what happens when there's only classical communication between the two parties. And it turns out that this is roughly controlled by the largest eigenvalues of this operator m. So along those lines, let's define m epsilon as m, but with all the eigenvalues that are sufficiently small zeroed out. Well, let's give an example. So let's say that we have an operator with eigenvalues 1, minus 1, and epsilon over 3. Well, then 1 and minus 1 are reasonably large. Epsilon over 3 is pretty small. And we're just going to say, okay, we can ignore this. This is small enough that it doesn't really impact our problem very much. And instead, effectively, what we're going to concern ourselves with is estimating this generalized inner product where we've replaced m with m epsilon. And you can show that this doesn't change the value very much, really just up to this error tolerance. The protocol that we will give that achieves our claimed upper bound is the following. So again, Alice gets k copies of her state psi. Bob gets k copies of his state phi. What they're going to do is first both project to the support of m epsilon. So these p epsilons here are going to be the projectors onto the supports of m epsilon. And they'll do this to all of the copies of their states. They'll receive SA and SB copies of the states. Then they'll independently perform the standard POVM in this metric subspace on the support of m epsilon. So if you're not familiar with what this is, the standard POVM is sort of a uniform POVM over all states of the following form. So you take some state in the vector space, and then you take n copies of it. And once they've performed this measurement, they obtain outcomes U and V. Alice is going to communicate this classical bit string U and SA, so the number of successful projections that she observed, to Bob. And then Bob will compute this quantity W here, and will claim that this is fairly close with high probability to the true value. And what we can claim is the following. We can claim that the bias is upper bounded by epsilon over 2, plus something that scales like 1 over k. We can claim that the variance scales like 1 over k plus the square 2 norm of m epsilon over k squared, plus the fourth power of the 2 norm of m epsilon over k to the fourth. And then if you look at these two expressions, well, it turns out that if you take k to be roughly the maximum of 1 over epsilon squared, and the 2 norm of m epsilon over epsilon, then both the bias is reasonably small, and also the variance is reasonably small, and you can claim that you successfully get an estimate of the true inner product, generalized inner product, up to your epsilon with high probability. On the flip side, we can prove lower bounds which are not quite the same but fairly close. In particular, what we can show is the following. Well, first observation is that M epsilon is fairly similar in some sense to identity on support. And what we're going to do is reduce estimating the inner product to estimating this new sort of weighted inner product. And using this argument, we can show a lower bound of the maximum of 1 over epsilon squared and the 2 norm over the square root of epsilon. So notice that we have a bit of a separation here in that our upper bound scales like the 2 norm over epsilon, and there are lower bound scales like the 2 norm over the square root of epsilon. I should say that this is also partially just a choice of presentation. The actual bound that we get in the paper is in terms of the 1 norm, and if you do some conversions between the 2 norms for the sake of presentation, then you achieve this lower bound that we've listed here. The lower bound that's in the full text is potentially a bit tighter, and there's cases such as poly operators and also projectors on the subspaces where the true lower bound that we get is actually tight and matches the upper bound. But regardless, what we can say in general is that this more or less captures the sample complexity of this task. All right. And with that, I'll move on to the second part of this talk, which is inner product estimation with entanglement. So before we looked at just classical communication, but it's also interesting to ask what happens if there's quantum communication as well. And like I mentioned before, these tasks all then become very easy with lots of quantum communication. And in particular, what they can do is Alice can send over a copy of her state, and then Bob can just perform a swap test. And if Alice sends, say, just even a few copies of her state, then they can achieve a pretty good estimate of their product with just a few number of operations. So then the interesting question to ask is, what if there's very limited quantum communication? What if they have some but not much? Really, we want to ask, well, what if Alice couldn't send over full copies of her state? So then they couldn't just play this game where Alice just submits a few copies to Bob and then Bob just performs a swap test. And what we can prove is the following. Well, if you're allowed a q-dimensional quantum message, then the sample complexity goes as square root d over q. And this gives us a bit of a smooth trade-off between the sample complexity and the amount of entanglement that's shared. So let's go to the limit where q is very large. So when the limit where q is very large on the order of the dimension, you get that this is going to go down to a constant, which is, again, what we expect, because then you can just teleport and perform, say, the swap test. And in the regime where q is very, very small, say q is going towards 0, well, then this actually goes to square root d. I put square root d over q here, but when q goes to 0, this does not, in fact, go to infinity. This actually just goes to square root d. So then that recovers sort of the two extremes that we knew going into this. That is, when you have lots of entanglement, this is a very easy task. And when you have very little entanglement or truly no entanglement, this is a very difficult task. And really, if you would like to find some regime where the sample complexity, say, is now polynomial in the number of qubits, then what this says is that you have to actually be able to communicate a linear number of qubits. Really, that you need a lot of entanglement, actually, to get any real advantage. Just small amounts of entanglement don't really provide that much of an advantage in terms of sample complexity. And what we can prove is, on the flip side, if you have a constant number of quantum messages of dimension q, then the sample complexity k equals O of square root d over q is also sufficient. So these are not exactly the same statement. The first one is saying just with a single message effectively. And then the latter here is saying that if they're allowed multiple rounds of this communication. But regardless, this gives us sort of matching results. And I'll speak a little bit more on this upper bound in just a second. So what we have is the following. Alice and Bob are both going to divide the Hilbert space into many random buckets. And by this I mean the following. They're going to take some hard random unitary and some way of partitioning the Hilbert space into different subspaces, and then they're just going to move those around using the random unitary. they're each then going to project onto these buckets, these subspaces, and keep track of these collisions. And then let's say that a projected state is this psi tilde. Well, then when there are collisions, what Alice is going to do is send over those now projected states to Bob, and Bob will perform swap tests on these projected states. I'll speak on this slightly more detail. So what Alice is going to do is she's going to start with her states which live on this d-dimensional Hilbert space, and she's going to project them onto a q-dimensional Hilbert space. And to do this, what we're going to do is fairly straightforward. So say that you just fix some q-dimensional projector, P, and you take a Haar random unitary U. Then if you apply this to psi, project onto the subspace, then you'll get something that now lives on a fixed q-dimensional random subspace. And of course, this doesn't succeed with probability 1, but with some non-zero probability, you'll actually successfully perform this projection. And let's say that Bob does the same and also successfully performs this projection. Then really the key point is that if you perform these sorts of random projections, then the fidelities are maintained with very high probability. So then what Alice can do is just teleport over this state, which now lives on a much smaller space, on a q-dimensional state, to Bob. And Bob will just perform a swap test. And this estimate that he will receive here will actually be fairly close to the true value with high probability. But of course, these projections do not succeed with probability 1. So what they're going to do is, again, this bucketing strategy where they maintain some number of projected states and keep track of collisions. All right, and that leads me to the end of the technical section. So I just want to summarize what I've spoken about and list a few open problems. So to summarize what I spoke about, number 1, we have the regime where you only have classical communication, and you would like to estimate this generalized form of inner product. And what we're able to show is that this is roughly controlled by the 2 norm of this m epsilon operator, which again is m, but with all the eigenvalues smaller than epsilon over 2, so just relatively small, replaced with 0. And then we also looked at estimating the inner product with limited amounts of quantum communication. And you can sort of think of the takeaway from this section being the following. Entanglement can help when we prove smooth lower bounds with respect to the amounts of quantum communication / entanglement, but it can't help a ton. Really, you need a good bit of it to really achieve very small sample complexity. And I want to leave you with a few open problems from our work. The first is the sample complexity of estimating the trace distance of mixed states using just LLCC. Without locality constraints, so if you're allowed arbitrary operations, then it's known that theta d copies are both necessary and sufficient. But our question is this sufficient with just LLCC as well? That is there an LLCC protocol that achieves sample complexity O of D? This may be the case, and if it is, it would illustrate an interesting difference between pure states and mixed states. Namely, for mixed states, we know that estimating inner products, which would then effectively give you 1 norms, can be done with a constant number of copies if you have entangled measurements. But we also know that if you're only allowed LLCC, then the sample complexity is theta square root d. So for mixed states, it turns out that the sample complexity is identical to estimate the trace distance. This would exhibit an interesting difference between the two. Another thing I want to mention is just more broadly how this is related to oblivious quantum state compression. And what do I mean by this? Well, I mean that say you're given k copies of a quantum state, and you want to compress this in some way where you don't actually know what rho is effectively. And there's existing techniques, and one part of our method with entanglement was really effectively just using state compression. But a good question is if you can compress multiple copies of a state better than you could with single copy compression schemes. And then lastly, I want to ask if generalized inner product estimation, so again, we have this operator M in here, can be achieved with entanglement in some way that you get an interesting trade-off in the sample complexity. So what we had given really is just with classical communication. And then for the case of M being identity, we were able to extend this to allowing shared entanglement as well. But interesting question is if this can be extended to more general forms of error products. And with that, I'll conclude my talk. If you have any questions or comments, please feel free to contact me at my email, which I've listed here on the slide. That is louisms2@illinois.edu. And thank you for listening.
Okay. Yeah, that was Louis Shatsky from University of Illinois, Urbana-Champaign. So it was a shared work between Srinivasan and Louis was actually the speaker. He's with us. So questions, guys. I'll just come.
Hello. So in order to use a protocol, do I have to already have diagonalized M in order to throw away the lowest eigenvalues? If so, like how does that cost influence your algorithm?
Right, yeah. Ooh, excuse me. Right, we are assuming that you know the basis for M so that you can throw out the subspaces that are effectively sort of not influential enough. That doesn't affect the sample complexity in any way, though, because, of course, this is just something that's kind of fixed in advance.
Yes.
Right?
But then,
it could affect the time complexity, certainly.
yes, time complexity, yes, correct. Also, just a second question. When you allow quantum resources in the communication, that looks to me, it looked a little bit similar to classical shadows when you can have like a quantum RAM. So there you can do like Bell measurements, and you could do state tomography or a purity measure or fidelity estimation more or less at the same cost. Have you looked into the similarities of both scenarios?
I mean, I think there are underlying similarities. I mean, of course, you could think of shadows as being some sort of compression in some sense, I suppose. I think there are underlying similarities. There is, it's also worth mentioning that there was a work that came out around the same time as ours that had some similar results, and their protocol was, part of it was with shadows, if I recall correctly. So I think there are obviously a lot of similarities. Yeah.
Okay, thank you.